In this second week on special relativity, we focused first on energy and momentum and showed that the conserved energy is gamma mc squared, with gamma being the Lorentz factor, and the conserved momentum is gamma mv. This expression gives back the non-relativistic energy and momentum when we take small velocity, except that for the energy we have an additional constant, which is mc squared, giving the famous E equal mc squared of Einstein. So we used this, what we have done in relativity in the context of particle physics. And we discussed why particle physics requires relativity. Basic example is annihilation of an electron and a positron into a muon and an antimuon. Once you do the math, you see that the gamma of the electron and positron has to be much greater than 1, so we are relativistic clearly. We have discussed the fundamental interactions, the first one being the electromagnetic interaction, mediated by the photon between charged particles. You have an example here of a photon hitting an atom and producing pairs of electron-positron. The other fundamental interaction is a strong interaction. It is responsible for the binding of quarks and gluons inside the nucleons, and then producing a nuclear interaction between the nucleons, which is itself responsible for the atomic nucleus. The weak interaction was introduced to explain beta decay. That's a radioactive decay in which an electron or a positron is emitted, but the electron didn't have enough energy according to energy conservation, and therefore a new particle interacting weakly with other particles was introduced, and that was a neutrino. The last particle of the Standard Model to be discovered in 2011 was the Higgs boson. It is responsible for the mass of the fundamental particles. However, in total, it only accounts for a small part of the mass of the object around us, because a large part of this mass comes from the interaction between the particles, and in particular between the quarks and the gluons, due to the E equal mc square equivalence between energy and mass. This is the largest contribution to the mass around us.